Electric wires are one of the most essential components of modern civilization, silently carrying power through homes, factories, cities, vehicles, and entire nations. Yet behind every simple-looking cable is a highly controlled industrial process that transforms raw metal into safe, flexible, high-performance conductors designed to operate for decades without failure. What begins as solid copper locked inside rock must be refined, melted, stretched thinner than a pencil lead, insulated with precision polymers, tested under extreme conditions, and wound at high speed before it ever carries electricity. And today on the How Factory, we're going inside wire manufacturing plants to see exactly how electric wires are made. From copper to power lines. The story of electric wire begins long before electricity itself. Humans have used copper for thousands of years because it is soft, workable, and resistant to corrosion. When scientists in the 18th and 19th centuries began experimenting with electricity, copper quickly proved ideal for conducting electric current efficiently. As power grids expanded and electric motors, lighting, and communication systems emerged, demand for copper wire exploded. Today, wire manufacturing is a massive global industry built around precision metallurgy, mechanical forming, and polymer science. The process begins at copper mines, where copper ore is extracted from the ground using open pit or underground mining. The ore contains copper bound to sulfur and other elements, and it must be processed extensively before becoming usable metal. At concentrator plants, the ore is crushed and ground into fine particles, then treated using flotation systems that separate copper-rich minerals from waste rock. The result is copper concentrate, which is shipped to smelters for refining. At the smelter, copper concentrate is heated in furnaces where chemical reactions remove sulfur and impurities. The copper melts and separates into layers, producing blister copper that is around 98 to 99% pure. This molten copper is then cast into large slabs or sent directly to electrolytic refining. In electrorefining, copper plates act as electrodes submerged in an electrolyte solution. When electric current passes through the system, pure copper dissolves from one electrode and deposits onto another, forming cathodes that are 99.99% pure. This ultra-pure copper is essential for electrical applications because impurities increase resistance and heat buildup. Once refined, copper cathodes are transported to wire rod mills, facilities that convert solid copper into long, continuous rods. At the rod mill, cathodes are melted in large furnaces and continuously cast into thick copper bars. These bars are immediately fed into rolling machines while still hot. Rolling mills squeeze and shape the copper into long rods, typically about 8 millimeters in diameter. This continuous casting and rolling process produces kilometers of uniform copper rod without joints, which is critical for reliable wire production. After cooling, copper rods are coiled and sent to wire drawing facilities. Wire drawing is where copper truly becomes wire. Rods are fed into drawing machines that pull the copper through a series of progressively smaller dies made from extremely hard materials like diamond or tungsten carbide. Each die reduces the diameter slightly, and by passing through many dies in sequence, thick rod is transformed into thin wire. This process elongates the copper while reducing thickness, aligning the metal's crystal structure, and improving conductivity. Drawing copper generates heat and work hardens the metal, making it stiff and brittle if not managed properly. To restore flexibility, wire is periodically annealed. Annealing involves heating the copper to a controlled temperature, then cooling it slowly. This relieves internal stress and restores ductility, allowing the wire to bend without breaking. Many modern drawing lines integrate continuous annealing systems so wire can be softened while moving at high speed. Depending on the application, wires may be drawn to different diameters. Household electrical wire is thicker for safety and current capacity, while electronics wire can be extremely thin. Some wires are single solid conductors, while others are stranded, made by twisting many fine wires together. Stranding improves flexibility and fatigue resistance, especially for cables that move or vibrate. Stranding machines twist multiple copper wires into precise configurations, controlling lay length and tension to maintain uniformity. At this stage, bare copper wire is complete, but it cannot be used safely without insulation. Insulation prevents electrical shorts, protects users from shock, and shields the conductor from environmental damage. Insulation materials are chosen based on voltage, temperature, flexibility, and application. Common materials include PVC, polyethylene, cross-linked polyethylene, rubber, and specialized polymers for high-temperature or outdoor use. Insulation is applied through extrusion. Copper wire is fed into an extruder where molten plastic is forced around the moving wire through a die. The plastic coats the wire evenly, forming a continuous insulated layer. Cooling systems immediately solidify the insulation, locking it into shape. Thickness must be exact. Too thin and insulation may fail under voltage. Too thick and the wire becomes bulky and expensive. Sensors monitor diameter, concentricity, and surface quality in real time. Some wires require additional layers. Power cables may include multiple insulated conductors twisted together, wrapped in fillers, shields, and outer jackets. Shielding, often made from braided copper or aluminum foil, protects signals from electromagnetic interference. Armored cables include steel or aluminum layers to protect against physical damage in underground or industrial installations. For multi-conductor cables, individual insulated wires are twisted together using cabling machines. The twist pattern ensures flexibility and prevents stress concentration. Fillers may be added to maintain round shape, and binding tapes hold everything together before the outer jacket is applied. The jacket, extruded similarly to insulation, protects the entire cable from moisture, UV light, chemicals, and abrasion. Throughout manufacturing, testing is constant. Electrical resistance is measured to verify conductivity. High-voltage tests check insulation integrity by applying voltage far beyond normal operating levels. Spark testers detect pinholes or insulation defects as wire moves along the line. Mechanical tests measure tensile strength, elongation, and flexibility. For power cables, thermal tests simulate years of heating and cooling to ensure long-term reliability. Once production is complete, wires and cables are wound onto reels or spools. Large power cables are stored on massive wooden or steel drums that can weigh several tons. Smaller wires are coiled automatically. Packaging protects the product during transport and storage, and labeling provides information about conductor size, insulation type, voltage rating, and compliance with safety standards. Different applications require different wire designs. Building wiring must meet fire resistance and safety codes. Automotive wiring must withstand heat, vibration, and chemicals. Power transmission lines use aluminum or aluminum steel reinforced conductors rather than copper, because aluminum is lighter and cheaper for long spans. These conductors are produced using similar drawing and stranding methods, but with additional steel cores for strength. Sustainability plays a major role in wire manufacturing. Copper is highly recyclable, and a significant portion of wire production uses recycled copper without loss of performance. Scrap wire is collected, stripped of insulation, melted, and refined back into pure copper. Modern plants are designed to recover materials and reduce waste, because copper is both valuable and energy-intensive to produce. What makes electric wire manufacturing remarkable is the balance between simplicity and precision. A wire looks basic, but it must meet exact electrical, mechanical, and safety requirements. It must bend without cracking, conduct efficiently without overheating, resist moisture and chemicals, and last for decades inside walls, underground, or exposed to the elements. Achieving that reliability requires constant control over chemistry, temperature, geometry, and cleanliness. From ore pulled out of the earth to cathodes refined to near perfection, from molten copper cast into rods to wire drawn thinner and thinner, from plastic extrusion to high-voltage testing, the journey of an electric wire is a hidden industrial process supporting everything that uses power. Every light switch, motor, computer, and power grid depends on these cables doing their job flawlessly. And that is exactly how electric wires are refined, cast, drawn, annealed, insulated, tested, and shipped, transforming raw copper into the power lines and cables that keep the modern world running. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and factories behind everyday technology.